Right, hi all, welcome to Moyo Math, and today we are going to be continuing with our crash course. We know that exams is right around the corner, so what we want to do is to ensure that we cover all those key topics that we need to know to prepare us for the examination. Don't forget to subscribe to that channel, share and like. So today what we're going to do, we're going to be looking at a key component in that mathematics exam, and that is dealing with trigonometry, dealing with the use of Pythagoras theorem, the use of trig ratios, sine, cos, tan, the use of the sine rule, cosine rule, and applying that to bearings, making sure that we understand bearings and how to answer questions involving bearings. And then we are also going to look at, under that geometrical component, circle theorems, ensuring that we know all the theorems and can apply those theorems to questions. And also with regards to circles, understanding with circles how to treat with questions involving area of a sector, length of arc, etc. So the geometrical component is an important component. We normally see it in the latter part of the exam, and we want to ensure that this crash course can assist us to answer such questions if it's seen in the exam in the next few weeks. So let's get into it. So starting off with a quick recap of Pythagoras theorem. So we know Pythagoras theorem, it deals with a right angle triangle, and we know that this triangle will have three sides. Call this side C, call this side A, call that side B, and we know Pythagoras theorem is one whereby we're going to create an important formula from the theorem, and that formula is the hypotenuse squared is equal to the sum of the squares of the other two sides. Bearing in mind that the hypotenuse is always understood as the side opposite the right angle. It is also the longest side of that right angle triangle, but we recognize it easily as the side opposite the right angle. So we know side C here will be our hypotenuse. So we can easily create an equation from this. Our hypotenuse squared, that's C squared, is equal to the sum, addition, of the squares of the other two sides. The other two sides in this right angle triangle, and it doesn't matter the order, it's going to be A squared plus B squared. So making sure when we have a right angle triangle that we can implement this very important theorem called Pythagoras theorem, and it is implemented when we have information for two sides of that right angle triangle and we need to determine the third. Of course, we're going to look at some questions to show where it is applicable. Also, when we have a right angle triangle, it's important for us to recognize our trigonometric ratios. So again, this is applicable to a right angle triangle. So when I have a right angle triangle, we know we can use our trigonometric ratios to help us to determine the length of a side or the size of an angle, an acute angle in that right angle triangle. And of course, with those trig ratios, we have to remember sine theta, which is equal to side opposite. So side opposite over the hypotenuse. We have cos theta, which is equal to side adjacent over hypotenuse. And we have tan theta, which is equal to side opposite over side adjacent. Of course, side opposite, we often write it as OPP over the hypotenuse HYP, We know cos theta is side adjacent, which is ADJ. So we abbreviate ADJ over HYP. And tan theta is equal to side opposite over side adjacent. And most students remember our trig ratios by using SOHCAHTOA. But it's also important us just remembering our trig ratios, we must recognize from that right angle triangle what side is the hypotenuse, what side is the opposite side, what side is the adjacent side. And of course, from this right angle triangle, we always know that the side opposite the right angle, it is the hypotenuse. So hypotenuse. The side opposite the angle theta, that acute angle, so this is our acute angle theta. So the side opposite that acute angle theta is known as our side opposite, which we can write as OPP. And the remaining side of that right angle triangle will be our side adjacent. So this is our side adjacent, or ADJ. So remembering, very important, how to label the sides of the right angle triangle. Again, using our angle theta to help with recognizing what side is opposite. Using the right angle for us to recognize what side is the hypotenuse and the remaining side being the adjacent side. Also recalling our very important trig functions, sine, cos, tan, and their corresponding trig ratios. So sine opposite over hypotenuse, cos adjacent over hypotenuse, tan, theta opposite over adjacent, or otherwise known as SOHCAHTOA. So let us apply this knowledge to a few questions to make sure we can apply what we have just recalled, which is our Pythagoras and trig ratios, to answer such questions. So let's again. So let me erase. So let's look at this question. It says here, the diagram below, not drawn to scale, shows a triangle LMN, that's our triangle, with LN equal to 12 centimeters, NM equal to X centimeters, and angle NLM is equal to theta degrees. So this is our angle NLM, theta degrees. It says here the point K on LM is such that NK is perpendicular to LM. NK is equal to 6 centimeters. So we see NK 6 centimeters and KM equal to 8 centimeters. So KM 8 centimeters. They want us to calculate the value of X. So this is X. So we need to find X. So if we look, X falls within a right angle triangle. That right angle triangle is NKM or MKN. Any one of the two we can use to name that right angle triangle. And in that right angle triangle, what we observe? We have information for two sides to help us to determine the third side. And once we recognize when we have information for two sides to determine the third, this is where Pythagoras theorem will come into play. So once a right angle triangle is observed, two things must come to mind automatically. The use of Pythagoras theorem or trig ratios. But again, what Pythagoras theorem is only used to determine the length of a side of the right angle triangle, provided two other sides are given. So we see where two other sides are given, and what we can use to determine the third side using Pythagoras. So for part 1, to find X, I'm going to start by naming the triangles. I'm going to say in triangle NKM or MKN, however you choose to name it, we're going to begin by always Pythagoras theorem. We begin with the hypotenuse squared. So the hypotenuse in this case will be NM squared. So I'll use the vertices to name the length is equal to the sum addition of the squares of the other two sides. And in any order, it doesn't matter. We can put km squared plus kn squared. After creating an equation, let's substitute. We're going to replace nm with x in brackets squared. We're going to replace km with 8 in brackets squared. Plus we're going to replace kn with 6 in brackets squared. And therefore x squared is equal to 8 squared, which is 64, plus 6 squared, which is 36. And therefore x squared is equal to 64 plus 36, that is 100. And we can easily find x by finding the square root of 100. So the length x is equal to 10 centimeters. So the length of x here will be 10 centimeters. So the use of Pythagoras theorem tells us to determine the length of side x. Let's look at part 2. We want to determine the size of that angle theta. So this is our angle theta. So to find that angle theta, we know that again a right angle triangle is observed, and when you have a right angle triangle, two things will come to mind: Pythagoras theorem or your trig ratios. But to find an acute angle in that right angle triangle, we are not going to use Pythagoras. Pythagoras is only used to determine the length of a side, so therefore our trig ratios will come into play. So in using our trig ratios, we begin by labeling the size of that right angle triangle. If this is theta, the side opposite to theta, and we're focusing on the triangle NKL or LKN, and in labeling, the side opposite theta will be known as side opposite. The side opposite the right angle, keeping in mind that this here is a perpendicular line NK, which will meet LM at right angles. So we know that the side opposite to that right angle will be the hypotenuse. So I'll use HYP, and the remaining side of that right angle triangle will be the adjacent side. So how do we know which one of the three trig ratios we're going to use? And in this case, because we want to find theta, to find an angle, we must have information for two sides to find that angle theta. And what two sides we have information for, and what we can do is to circle the two sides we have information for. The two sides we have information for are opposite and hypotenuse, and the trig function that links opposite and hypotenuse will be sine theta. So we can state here sine theta is equal to our side opposite all over the hypotenuse. Sine theta is equal to our side opposite, which is 6 centimeters, over the hypotenuse, which is 12 centimeters. So the two sides we have information for, and therefore to get theta by itself, we have to remove sine, and keeping in mind 6 over 12 is the same as a half, and to get theta by itself, remove sine, which comes across to the other side of the equal sign. So this sine theta. So we're going to remove sine, which comes across to the other side of the equal sign in order for me to get theta by itself. So this is sine theta is equal to half. But to get theta by itself, I'm going to remove sine. And when that sine comes across, it comes across to the right as sine inverse of a half. And sine inverse of a half is equal to 30 degrees. So showing where our use of Pythagoras and the use of our trig ratios can come into play to assist us. Let's look at another question to highlight the use of Pythagoras theorem and trigonometry. What we're also going to do today with this crash course is to understand and recognize two other very important rules, sine rule and cosine rule. And those two rules are applicable to a triangle that is not right angle. So we want to make sure that we understand how to apply our sine and cosine rule to a non-right angle triangle. So let's look at another question. So let's look at this question. So with this question, it says the diagram below, not drawn to scale, shows two straight wires. The two straight wires are LJ, so we see LJ, and NK. So we see how two straight wires supporting a vertical pole MJ. So these two wires are supporting a vertical pole. It states LMN, so LMN is a straight line on a horizontal plane. Angle JML is 90 degrees. Angle KNM is equal to 30 degrees. LJ is 30 meters, LM 5 meters, and KN 10 meters. So you want us to determine the length of MK. So where is MK? So let's recognize where is MK. So this is MK. So to find MK, if we look, MK falls within a right angle triangle. And again, when you see a right angle triangle, what should come to mind automatically? Either Pythagoras theorem or trigonometry. But let's see which of the two we're going to use. So with that right angle triangle, we do not have information for two sides to find the third. So Pythagoras theorem is out. We see an acute angle, we see a side of the right angle triangle, so automatically we know in this case our trig ratios will come into play. So our trig ratios will be either sine, cos, or tan, but first to recognize which, we have to label. So if this is my acute angle 30, the side opposite 30 will be, in this right angle triangle, will be side opposite. The side opposite the right angle, this is my right angle. I have my vertical meeting the horizontal, so that's 90. So the side opposite the right angle is the hypotenuse, and the remaining side will be the side adjacent. So for us to find the length of MK, again, we are going to circle, and this will help to recognize which trig function you're going to use. You circle, in this case, the side you have to find, which is MK, and you circle the side you have information for, which is hypotenuse. And the trig function that links the two that I've circled will be sine theta. So we're going to put here part 1, sine theta, and I'm going to name the triangle first, in triangle KMN or MNK. We're going to simply state sine theta is equal to our side opposite all over the hypotenuse. So sine, the angle theta is 30 degrees, is equal to our side opposite, which is MK, the side you have to find, over the hypotenuse, which is 10 meters. First to get MK by itself, we put sine 30 over 1, and we are going to carry out the whole process of cross multiplication. So we multiply 1 by MK to give us MK, and we're going to multiply 10 by sine 30 to give us 10 multiplied by sine 30 degrees. And sine 30 is equal to a half, MK is equal to 10 by 0.5, and 10 by 0.5 will give us 5. MK is equal to 5 meters. So having found MK, let's look at part 2. Part 2, we have to determine the length of JK. So where is JK on our diagram? This is JK. So to find JK, again, we put some thought into it. Clearly, we just found the length of MK. And to find JK, if I find the length of JM, if I find the length of JM, and I subtract from the length of JM the length of MK, which we just got previously to be 5 meters, then I can easily determine what's the length of JK. So the objective now is to find the length of JM or MG. And JM or MJ falls within this right angle triangle, which is JML or LMJ, how we choose to name the triangle. So let's use that right angle triangle to help us to find the length of JM or MJ. And in looking at that right angle triangle, what we observe? Again, what is a right angle triangle? What should come to mind? Pythagoras theorem or trigonometry. And in this case, if we look, clearly we're going to use Pythagoras theorem because we have information for two sides to determine the third side. So let's use Pythagoras theorem. So using Pythagoras theorem, remember with Pythagoras, we begin with what? The hypotenuse square. The hypotenuse in that right angle triangle is the length JL or LJ. So I put JL squared is equal to the sum of the squares of the other two sides. And again, it doesn't matter the order. So I'm going to put first LM squared plus JM squared or MJ squared. Let's substitute the hypotenuse. We know that JL it is 13 meters. So I'm going to put 13 in bracket squared. I'm going to replace LM with 5 in bracket squared plus JM squared. 13 squared, of course, will be 169. 5 squared will give us 25 plus JM squared. We're going to subtract 25 from both sides, so it's going to be 169 minus 25 is equal to JM squared. We subtract 25 from 169 to give us 144 is equal to JM squared, and therefore JM will be the square root of 144. JM is equal to 12 meters. So we know that the length of JM, we just worked that out to be 12 meters. So I'm going to put my 12 meters here. So that represents JM. So having found JM, we can easily now find JK. So we put JM. Let me write JM here. So this is my hypotenuse. So therefore, having found the JM, which is 12 meters, and having found KM or MK, which is 5 meters, what we can do now is to determine the length of JK by subtracting 5 from 12. So we can state, therefore, and the three dots means therefore JK is equal to JM minus KM or MK. JM, it is 12 meters minus KM, which is 5 meters. And therefore we have 7 meters as the length of JK. So ensuring that we understand the use of Pythagoras, the use of trig ratios, both are applicable to a triangle that is a right angle. So let's look at now a case where the triangle is not right angle. And this is where two very important rules will come into play. That is the sine rule and that is the cosine rule. So let's look at those two rules. Right, so what we're going to do is to look at cases where the triangle is not right angle, and this is where we're going to apply what we call the sine rule and the cosine rule. So let's look at first a quick review of what is the sine and the cosine rule. So the sine rule, we have a triangle and that triangle is not right angled. We have three vertices A, BC. And we have three angles. Call this angle A, call this angle B, call that angle C. In using the cosine rule or the sine rule, what is important for us to do is to begin by labeling the sides of the triangle. So to label the sides of a triangle where we are applying both the sine or cosine rule, what we are going to do is label by first looking at the side opposite the given vertices. So if we have vertex A, the side opposite to vertex A, we're going to label that common A. So the side opposite to the vertex, we use the common letter. So if this is vertex B, the side opposite to vertex B, we're going to label that common B. And if this is vertex C, the side opposite to vertex C, we call it common C. And the sine rule, it is simply creating ratios. So our first ratio we can simply write as A over sine the corresponding angle at A is equal to common B over sine the corresponding angle at B is equal to common C, side common C, over sine the corresponding angle at C. So this is the sine rule, very important rule that we must ensure we know for a triangle that's not right angle. What about the cosine rule? So again, for the cosine rule, let's draw another triangle, and that's labeled same A, B, C. So we have those three vertices. We have three angles, angle at A, angle at B, angle at C. Again, to label, we begin by labeling. Look at the vertex, and the side opposite that vertex, we use the common letter. So if it's the vertex at A, the side opposite will be common A. Vertex at B, the side opposite we label common B. Vertex at C, the side opposite we label common C. And the cosine rule is normally an equation created provided we have two sides that are known and an included angle. So suppose we want to find side A, for example, and we're given information for side B and side C. Once side B and side C meet to form this included angle A, then automatically we're going to use a cosine rule. So this is my side A. I look opposite and I see I have information for my two sides, and once those two sides meet to form this angle, that angle is known as the included angle. So I'm going to simply create here for my cosine rule, it is going to be side A squared is equal to B squared, which are my two known sides, plus C squared, minus 2BC, two known sides, cos my included angle at A. So this here is, of course, the representation of the cosine rule. Suppose we want to find side B, and opposite to side B we have two sides that are known to us. We know those two sides, we have information for those two sides, and those two sides meet to form this included angle at B. Then again the cosine rule can be used. So I'm going to create my equation by stating B squared is equal to, I look opposite, A squared plus C squared minus 2AC cos the included angle at B. Or if C is my unknown side and opposite to side C, I have information for two known sides and an included angle. Keeping in mind what's the included angle, where two sides meet to form that angle, it's known as the included angle. Then I can create my equation, which will be C squared is equal to my two known sides, A squared plus B squared minus 2AB cos the included angle at C. So these two rules are very important rules, and of course they are used in a triangle more so that is not right angled. So let's look at a question where we can apply our knowledge of the cosine and sine rule. So let's look at this question. So we have this diagram. On the diagram below, not drawn to scale, TU, so TU is 8 meters, TW 10 meters, BW 11 meters, and angle UTW 60 degrees. An angle UV 40 degrees. They want us to calculate the length of UW. So to determine the length of UW, this is UW. UW clearly falls within two triangles. One triangle, it is UTW. The other triangle, we can label it UVW. And in looking at both triangles, clearly the triangle on the left will have sufficient information to help us to find the length of UW. Because if we look at that triangle on the left, opposite to UW, what do we observe? We observe two sides that are known to us, and those two sides meet to form this angle which is known as your included angle. And once we observe that, automatically the cosine rule will come into play. So we're going to label the sides. This here is capital T, so the side opposite will be common T. This is capital W, so the side opposite will be common W. This is capital U, the side opposite will be common U. And we can create an equation from that. So part 1, using the cosine rule, we're going to begin with common T squared. So remember, UW is also common T. So common T squared is equal to the two sides that are known to us opposite to common T, which are U and W. So we're going to write U squared, and it doesn't matter the order, plus W squared minus 2UW cos the included angle at T. So having stated our equation, our next step will be to substitute. This will be T squared is equal to U, which is 10 in brackets squared, plus W, which is 8 in the brackets squared, minus 2 times U, which is 10, times W, which is 8, cos the angle at T, which is cos 60 degrees. We're going to get T squared is equal to 100 plus 8 squared will be 64. And this here now will be negative 2 by 10 is negative 20, and negative 20 by 8 will be negative 160 cos 60 degrees. In simplifying further, we're going to get what? T squared is equal to 164 minus 160 cos 60 degrees. And we have to be very careful at this point, because what students often do, they often subtract 160 from 164 and they will multiply that result by cos 60, and that's incorrect. Remember, your 2UW cos T in this case, it is one term. So it means here that your, well, this is negative 160 cos 60 degrees, that is also one term. So what we have to do is to work out this entire thing, and then we're going to subtract that result from 164. So this will be T squared is equal to 164, subtract, let's work out what is 160 cos 60 degrees. So we go to our calculators, make sure your calculator is in degrees, and this will be 160 multiplied by cos 60 degrees, and that will give us 80. So this will be 160 cos 60 will give us 80. And therefore t squared will be equal to 80 from 164 will give us 84. And to find the t will be equal to the square root of 84. We can go to our calculators, and the square root of 84 will give us, that will give us 9.16. So t is equal to 9.16 meters. And we can approximate to the nearest whole. If we approximate to the nearest whole, because nothing was stated in terms of what we can approximate our answers to. So we can approximate to the nearest whole, make sure it's stated in brackets. So t or uw to the nearest whole will be 9 meters to the nearest whole number. So the length of uw is equal to 9 meters. So let's look at part 2. Part 2, they want us to find the size of angle UVW. So angle UVW. So ensuring we know where that angle is located. Remember, the angle is always located at the letter located at the middle. So that's where the angle will be positioned. The letter at the middle. So looking at UVW, this is our angle here. So we're looking at that letter at the middle. So we want to determine what is that angle UVW. So let's proceed to find that angle. So keeping in mind this is 9 meters. Let me put that on the diagram. So we know that the length of UW is 9 meters. So to find that angle exists within that triangle located to the right, which is UVW. So in that triangle, clearly we know that it's either sine or cosine rule. We cannot use trigonometry because it's not right angle. So it's either the sine or cosine rule. And to find that angle, we know that the sine rule will be used automatically. Because the sine rule is used when it comes to finding an angle. We must have information for two sides and an angle, not an included angle, but an angle. So an included angle is where two known sides meet to form that angle. We have two known sides, yes, but those two known sides do not meet to form that included angle or that angle at 40 degrees. So when two known sides meet to form an angle, then that angle is known as an included angle. 40 is not an included angle. So once we have two known sides and an angle, which is not an included angle, then obviously we're going to use what the sine rule to assist us. So we're going to state here part 2 in triangle UVW using the sine rule. We begin by labeling the sides. So if this is vertex V, the side opposite to vertex V will be common V. If this is vertex U, the side opposite will be common U. If this is vertex W, the side opposite will be common W. And to create our equation for the sine rule, I like to begin my equation for the sine rule by, and keeping in mind the sine rule is about ratios. So my first ratio will always have the unknown. My unknown is the angle at what? V. So my first ratio will involve everything involving V. So it's going to be common V over sine the angle at V. So my unknown, my first ratio will have my unknown. The unknown is the angle at V. So my first ratio will involve V. So the side common V over sine the angle at V is equal to My other ratio is one where I must have information for both side and angle, corresponding angle. So, in looking at that triangle, where do I have information for side and corresponding angle? That will be U, where I have information for side, 11 meters, and the corresponding angle, that angle opposite to my side common U, which is the angle at U, 40 degrees. I have information for that, so I can create my other ratio, common U over sine the angle at U. So I have created my equation here for the sine rule. So let me substitute into my rule. This will be what? This will be common V, which is 9 meters, over sine the angle at V. Keeping in mind the angle at V is what you want to find. That's your known, is equal to common U, which is 11, over sine the angle at U, which is 40 degrees. We have an equation with single fractions on either side. So at this point, we can cross multiply. So this becomes 11 multiplied by sine the angle at V, and it doesn't matter what side it's on, is equal to 9 multiplied by sine 40 degrees. This will become, I need to get sine the angle at V by itself. So this 11 in front of sine the angle at V must be removed. So I'm going to divide 11 to both sides. So when my two 11s divide into each other, I'm going to get, to give me 1, I'm going to be left with sine V, sine the angle at V, and then I go to my calculator. Let me work out what is 9 multiplied by sine 40 over 11. So I use my calculator, start with brackets, and I'm going to put 9 multiplied by sine 40. So start with open brackets, 9 multiplied by sine 40, close brackets. My division sign, my vinculum also represents the division operation, divided by 11, which will give me 0.5259. And we can take about 3 to 4 places after the point because it helps us to get a better approximation to our answer. You don't have to put down all the digits on the calculator. Take about 3 to 4 places after the point. So to get V by itself, it means we need to remove sine. And when I remove sine, we know it comes across to the other side, and it's going to come across to the other side as sine inverse of the equal sign as sine inverse. So angle V is equal to sine inverse of 0.5259. And when we go to our calculator, we are going to simply press second function, sine. So I see sine to the power of -1 on my screen, sine to the power of -1. I'm going to put my open brackets and 0.5259, close brackets. So we should see something like this. Of course, equal sign, and we're going to get here 31. So the angle at V is 31.72 degrees. Remember, it's an angle, so we must put degrees. And I'm going to approximate it to the nearest whole. They didn't ask or specify to approximate to any number of significant figures or decimal places. So to the nearest whole, the angle at V will be 32 degrees. To the nearest whole number. Alright, so this here it is part 2. So let's look at part 3. Part 3, we are now asked to find the area of triangle TUW. So let me put 32 degrees as my angle I just found in my diagram. So the last part of this question, we want to find the area of the triangle TUW. So where's triangle TUW? TUW. So we want to find the area of that triangle. Now, to find the area of a triangle, and this is important to know because the area of a triangle is not only based by height over 2. We are familiar, once we have a triangle and there is a perpendicular height, so that perpendicular height meets your base, we know we can use the formula area is equal to base by height over 2. But when we look at our triangle, there's no perpendicular height. There's no perpendicular height. So that formula is out of the question. So what are we going to use to help us to find the area of that triangle? So part 3, to get the area of that triangle, we are going to use an important formula. And that formula, it is, if I have a triangle, I have 2 known sides again, and an included angle. This time, of course, to find the area of a triangle, once you have 2 known sides and an included angle, then to find the area of that triangle, we use this formula, half times side A, which is one known side, by side B, which is another known side, by sine the angle theta. So that's the formula we use to find the area of a triangle, provided you have 2 known sides and an included angle. So for part 3, so keep that formula in mind, let's find the size of the area, of angle T, UW. And when we look at that triangle, what we observe, what do we see? We see 2 known sides and an included angle. So once you see that, automatically what comes to your mind will be that important formula. So our area of that triangle will be a half times side U times side W by sine the angle at T. And let's substitute into that formula. A is equal to a half times side U, which is 10, times side W, which is 8, multiplied by sine the angle at U, which is 60 degrees. So this is A is equal to, and we go to our calculator, this is 2 into 2, 1, 2 into 10 is 5, 5 by 8 is 40, multiplied by sine 60 degrees. Yeah, so when we go to our calculator, 40 multiplied by sine 60, we are going to get the area of that triangle as 34.64 meters squared. And I will approximate the nearest whole number. So the area to the nearest whole, so approximate the nearest whole will be 35 meters squared to the nearest whole number. All right, so ensuring that we understand how to use what we call the sine rule and the cosine rule. So let's see if we can apply it to another question. This time I'm going to look at a question where we have a merge. We're looking at the use of Pythagoras where necessary, the use of trigonometry where necessary, and the use of the sine and cosine rule where necessary. So let's look at this question. So with this question, we have the diagram below, not drawn to scale, shows a vertical flagpole FT. So we have this vertical flagpole, and with its foot F on the horizontal plane EFG. So that horizontal plane is flat on the ground. So for example, my calculator is my horizontal plane, it's flat on the ground, and the vertical pole FT will be my marker. So the marker, the vertical pole, will meet your flat horizontal plane EFG, that triangle, right? And of course, once a vertical meets a horizontal, they meet at right angles to each other. Very important to note. So we have that vertical pole, it meets the flat plane. It says here that ET and GT are wires which supports the vertical pole. So we have this vertical pole and we have some wires supporting the vertical pole in its position. The angle of elevation, and again, very important for us to know with trigonometry, angle of elevation, angle of depression, which of course I'm going to review as part of this review exercise involving trigonometry, angle of elevation, angle of depression. So the angle of elevation of T from G, T from G is 55 degrees. So the angle of elevation means we have a horizontal line of sight, and when we look up, that's your upward line of sight. So the angle between the horizontal and upward line of sight is your angle of elevation, 55 degrees. It states EF is 8 meters, FG 6 meters, and angle EFG, so EFG is 120 degrees. They want us to calculate, given your answer correct, to 3 significant figures. So now 3 significant figures, so we know what we have to approximate our answer to. The height of FT. So this is FT here. Keeping in mind FT meets that flat plane at right angles. Good? So if we look to find FT, FT falls within 2 right angle triangles. One to the left and one to the right. But which right angle triangle will have sufficient information to help us to find the height FT? Clearly it's going to be the right angle triangle on the right, because we have information for a side and we also have information for an acute angle. So once we have a right angle triangle where we have information for a side and an acute angle, trigonometry can come into play to help us. We can't use Pythagoras because we do not have information for 2 sides to find that third. So trigs will automatically come into play. So we're going to label. But what I'm going to do is to pull out that triangle. So let's deal with it individually. 1. So I'm going to take out that triangle. So this here is your triangle FTG. This angle here, it's 55 degrees. We know that FG, it is 6 meters. So let's find the height of that flagpole FT. Again, using trigs, we're going to label. So the side opposite your acute angle, FT, will be side opposite. The side opposite the right angle is the hypotenuse, and the remaining side is the adjacent side. And if we want to find side FT, we circle the side we have to find, and we circle the side we have information for. So what trig function links those two that I've circled? Clearly tan theta. So in a triangle, and let me name the triangle TFG, we're using trigonometry. Tan, or trig ratios, tan theta is equal to side opposite over side adjacent. This becomes tan 55 degrees is equal to my side opposite, which is FT, which is what we want to find, over the side adjacent, which is 6. I put tan 55 over 1, and I cross multiply. 1 by FT gives me FT, and this is equal to 6 multiplied by tan 55. So FT is equal to 6, we go to our calculator, 6 multiplied by tan 55 will give us 8.568, and they want us to approximate our answer to 3 significant figures. So 8.568 meters. To approximate to 3 significant figures, remember, to 3 significant figures, we count from the first non-zero digit from the left, going from left to right. So we're counting 1, 2, 3. Third significant figure, we look at the number after, immediately after, which is 8. Once that number immediately after is 5 or more than 5, we're going to add 1 to our number before, which is 6 on the line. So therefore, this becomes FT is 8.57 meters to 3 significant figures. So that's our answer there for part 1. So let's look at now the length of EG. So where is EG? This is EG. So EG lies within that triangle EFG. And that triangle EFG is flat on the ground, right? FT, of course, is that vertical pole which meets your flat plane, flat horizontal plane. So if we have to determine the length of EG, this is EG here. If you look at that triangle, what do we observe? Opposite to EG what we observe? We observe two known sides and an included angle. So one time, what should come to your mind? Cosine rule. So the cosine rule is applicable to that triangle to help us to find the length of EG. So let's use the cosine rule and let's find the length of EG. So this will be what? So I'm going to erase. So part 2, in using the cosine rule, we know we're going to label the side. So this side will be what? If this is capital F, the side opposite will be common F. If this is vertex E, so vertex F, side opposite common F. Vertex E, side opposite common E. Vertex G, side opposite common G. So let's create our equation. I'm going to start by naming the triangle. So in triangle EFG, we are going to begin with using F squared, and let me state using the cosine rule. Common F squared is equal to common E squared plus common G squared minus 2 EG cos the angle at F. Let me substitute. F squared is equal to E, which is what? 6 in brackets squared, plus G, which is 8 in brackets squared, minus 2 times 6 times 8 cos the angle at F, which is cos 120 degrees. Making sure you remember our steps to the cosine. F squared is equal to 36 plus 64 minus 2 by 6 is 12, 12 8 are 96, cos 120 degrees. So this becomes F squared is equal to 36 plus 64 will be 100 minus 96 cos 120 degrees. What we are not going to do is subtract 96 from 100. So we are going to work out what is negative 96 cos 120. So this will be F squared is equal to 100. You can hold the subtraction sign and let's multiply 96 times cos 120. Right, so 96 by cos 120 will give us negative 48. So we make sure we put that negative 48 in brackets. So we hold the subtraction sign, multiply 96 by cos 120 to give us negative 48, and we put negative 48 in brackets to separate those two subtraction signs. So this becomes F squared is equal to 100 plus 48. F squared is equal to 148, and therefore F is equal to the square root of 148, and therefore the square root of 148 will give us 12.16. So we know that EG is equal to 12.165, and the three significant figures we count from the first non-zero digit from the left, 1, 2, 3. We look at the number after, which is 6. Once it's 5 or more, we add 1 to the number before, so that 1 becomes 2. So EG is equal to 12.2 meters. The three significant figures. Okay, so again, the use of the cosine rule to assist us, and again the use of trigonometry to assist with part 1. So let's find now the angle of elevation of T from E. So what's the angle of elevation? Angle of elevation, you have a horizontal line of sight, and if someone calls out to you, obviously you're going to look up. So when you look up, the angle between your horizontal line of sight and upward line of sight is your angle of elevation. So the angle of elevation of T from E. So from E, this is T from E. Of course, my angle of elevation, this is my horizontal line of sight, this is my upward line of sight, and this here will be my angle of elevation. So for me to find that angle, what am I going to do? Again, that angle falls within a right angle triangle. That right angle triangle, it is EFT or TEF. We found FT earlier, and we got FT earlier to be 9 meters. So what we can do, we have a right angle triangle where there is information for two sides, and therefore we can use those two sides help us to find the acute angle theta. So when you have to find an acute angle theta, you must have information for two sides, but you're using trigonometry. Yeah, you're not using Pythagoras, you're using trigonometry. So let us find that angle of elevation. So, using trigs, we're going to label the side opposite my angle at E will be side opposite. And let me pull out that triangle so we can have a better view of the triangle. So this here is my triangle TFE. TFE. So decide to pull it out. This will be, of course, this is my angle. This is my angle of elevation. I need to find that angle. This here, FT, it is 9 meters, which we would have worked out in part 1. This here, it is 8 meters. We have information for two sides, and we're using trigonometry to help us to find that acute angle. So, we label the side opposite the angle theta is my side opposite. The side opposite the right angle is the hypotenuse. The remaining side is the adjacent side. I circle the two sides I have information for, which is opposite and adjacent. What trig function comes into play automatically? Tan theta, which is equal to side opposite over adjacent. So tan theta is my side opposite, which is 9, over my adjacent, which is 8. And therefore theta is equal to tan inverse of 9 over 8. So I go to my calculator, shift tan, open brackets, 9 divided by 8, close brackets. We should see something looking like this. And when we press the equal sign, we should have gotten 48.366 degrees. But three significant figures, we count from the first non-zero digit from the left, 1, 2, 3. We look at the number after, which is 6. Once it's 5 or more, we add 1 to that 3 to become 4. So theta is equal to 48.4 degrees to three significant figures.